In this video, we're going to continue our discussion with the distribution of the sample mean. So let's take a look at a couple of examples. The Environmental Protection Agency rates the mean highway gas mileage of the 2013 Ford Edge to be 27 miles per gallon. Assume the standard deviation is 3 miles per gallon. A rental car company buys 60 of these cars. Assume this is approximately normally distributed and answer the following questions. So verify the requirements have been met for using the sampling distribution. So the two requirements are, number one, it's a simple random sample. As we go through more statistics techniques throughout this course, it's going to be extremely important at the problems that we're going to be looking at that they are simple random samples. And number two, 60, that's the sample in this case that the cars bought, is less than or equal to 5% of the population of 2013 Ford Edges. This makes sure the sampled values are independent of each other. Okay, let's take a look at part B. What is the probability that one randomly selected car has an average mileage greater than 26 5/10 miles? All right, so this is X is greater than 26 5/10, and in interval notation, I can write that as 26 5/10 to infinity. So this is still a normal CDF problem. It'll start with 26 5/10. It'll be 100,000. The mean, which is 27, and now the standard deviation now changes. It's the population standard deviation divided by the square root of n. Well, n in this particular case is 1, so it would be the square root of 1. So this is exactly what you would put into the calculator. So let's do that now. Okay, so let's put this in the calculator. So it'll be second and vars. We'll hit normal CDF. So the minimum is 26 5/10. Hit enter. Upper is 100,000. Hit enter. The mean for us is 27, and the standard deviation is 3 divided by the square root of 1. That's second x squared. There's 1. Close it. Highlight, paste, hit enter. And again, we'll round this to 4 decimal places, which is 0.5662. So let's put that on our paper now. Okay, let's take a look at part C. What is the probability that a random sample of 30 cars has an average mileage greater than 26 5/10? So it's still greater than or equal to 26 5/10. So what changes here? This is a normal CDF. Still 26 5/10 to 100,000. 27, and now it's going to be 3 divided by the square root of 30. Putting that into the calculator, you get 0.8193. Okay, let's take a look at part D. What is the probability that a random sample of 60 cars has an average mileage greater than 26 5/10? Normal CDF, 26 5/10, comma, 100,000, comma, 27, comma, 3, divided by the square root of 60. Putting that into the calculator, rounding appropriately to 4 decimal places, you get that. Okay, let's take a look at part E. There's a 10% chance of the mean highway gas mileage of a random sample of 60 cars will exceed what value? So I'm going to draw a bell curve first for this, and then we'll discuss further. So here's a drawing for the top 10%. Now, not asking for a probability and not asking for a proportion. So which calculator function am I going to put? And that's going to be inverse norm. But inverse norm only goes to the left-hand side. So I'll take 100% minus 10%, and that's going to be 90%. So it's going to be inverse norm of 9/10. The mean, which is still 27, and the standard deviation, that's 30. And it's talking about 60 divided by the square root of 60. All right, let's put that in the calculator now to see what we have. Okay, so second vars, We're looking for inverse norm, that's number 3. So area would be 9/10. The area is going to be 27. The standard deviation is 3 divided by the square root of 60. Okay. Paste. Hit enter. So we'll round this to 1 decimal place, so that'll be 27 5/10 miles per gallon. All right, let's put that on the paper. Don't forget to your unit of measurement for this problem. Okay, so in the last example, it specifically said it was normally distributed. Well, what happens if the distribution is not normal or it is unknown? Okay? Well, let's take a look at a couple of the pictures here. Okay? And if you notice one particular thing here, as the sample size for this increases, okay, what does the distribution look more and more like? So here, this is n is equal to 2. Here it's n equal to 12. And here it's n is equal to 20. So as that sample size of n is increasing, it becomes more and more normal. Okay? This is where the central limit theorem comes into play. Regardless of the shape of the underlying population, the sampling distribution of the sample mean becomes approximately normal as the sample size n increases. So how large does a sample have to be? Well, that depends on the distribution of the underlying population. Here's a good rule of thumb moving forward. If the distribution of the population is unknown or not normal, then the distribution of the sample mean is approximately normal, provided that the sample size is at least 30. This is going to be extremely important moving forward, so make sure you understand this. Okay, next page. If the distribution of the population is unknown, like the example we're going to look at below, the minimum size of the sample size must be 30. That will be the magic number for us. Okay, let's take a look at this example. The shape of the distribution of the time required to get an oil change at a 10-minute oil change facility is unknown. However, records indicate that the mean time for an oil change is 11 4/10 minutes, and a standard deviation for an oil change is 3 2/10 minutes. What is the probability that a random sample of 40 oil changes results in a mean time less than 10 minutes? Make sure to verify the requirements first. Okay, so I'm going to write out the first 2 requirements now. Number 1, it's a simple random sample. Number 2, 40 oil changes, or 40 is less than or equal to 5% of all the oil changes at this place. Now, nowhere does it say it's normally distributed, but take a look at what I care about here. We're talking about 40 oil changes. Well, 40 is greater than 30. Okay? So the central limit theorem will tell me the distribution of the sample mean is approximately normal. So I'm going to write that out now. So the sample size, which is 40, is greater than or equal to 30. So by the central limit theorem, the distribution of the sample mean is approximately normal, or the sampling distribution of the sample mean is approximately normal. Now that I know it's approximately normal, now I can use a normal CDF for this problem. Okay, less than 10, so that's x is less than 10. Interval notation, that's negative infinity to 10. So this is what? Normal CDF of negative 100,000, comma 10, comma, what the mean is, that's 11 4/10, divide, and comma, standard deviation, 3 2/10, divided by the square root of 50. Sorry, that should be the square root of 40, not the square root of 50. Okay, here I get this. Okay, part B, only difference is it's 50 oil changes instead of 40. So, normal CDF to 4 decimal places, that's this. Okay, part C. Suppose the manager agrees to pay each employee a $50 bonus if they meet a certain goal. On a typical Saturday, the oil change facility will perform 40 oil changes between 10 a.m. and 12 p.m. Treating this as a random sample, what mean oil change time would there be a 10% chance at being at or below? Now, is it asking for a probability? No. Is it asking for a proportion? No. So what calculator function am I going to use here? That would be inverse norm. Now, 10% or below, so the area would be 10% or 0.10, comma, the mean, which is exactly the same as it's been before, standard deviation, 3 2/10 divided by the square root of 40. 1 decimal place, that's 10 8/10 minutes.